Here's a topic about driving innovation with Servo and OpenHarmony. And there are two parts in this topic. The first part is unified rendering, and the second part is WebDriver. So I will introduce the first part. The second part will be introduced by my colleague, Zhizhen. Okay. Okay, let's come to the first part. So unified rendering of Servo in OpenHarmony. Okay, so let's take a look at the current rendering solution in Servo. So the data flow that maybe has mentioned by Martin and Oriol in the previous talk. So when we input the page will be passed into the DOM tree, and after style calculation and the layout, we get the fragment tree. And then the display list and the string context will be created based on the fragment tree. And then after the display list is created, it will send it to the compositor, then forwards it to the web render. And the web render will do the rendering work and display the contents on the page. Okay, so you can see that the display list is the main data structure between Servo and the two web render. And you can see there are many display items in the display list, such as rectangle, heat test, and something else. Okay, so it also contains items that are needed to build the property tree in the web render, such as here in the clip display item and the spatial tree item. Okay. So here, but in some certain scenarios that web render demonstrates some suboptimal performance, and we test that in the target page or mobile shopping homepage. That after layout, the display list sent to web render, and in web render there are two threads. The first one named SimBuilder, and the second one is render backend. So the SimBuilder receives the display list and will takes over about 15 milliseconds, and the second thread will receive the data come from SimBuilder, and it will take over 10 milliseconds, and then it will send it to GPU for the rasterization work. So we hope to achieve some vertical integration with OpenHarmony to optimize rendering performance. So in OpenHarmony, we have the render service. So render service is the core component of OpenHarmony graphic subsystem. It can reduce the GPU and the CPU workload through the techniques such as collision calling and minimal region updating. Okay, so you can see the picture below that different applications can use ArcUI, and ArcUI will do the command recording and send the command list to render service. And the render service will play back the command list and do the rendering work. And also, render service maintains a full render tree, so it can make full use of the multi-core processing capability of the device through parallelism. So how can we enable unified rendering in Servo with render service? As we mentioned before, that the display list is the main data structure between Servo and web render. So we try to reuse the display list defined by web render API. Okay, so here is a picture down below that before that the compositor will receive the display list. There is a channel here, and then it will send the display list to web render. And after our design, we replace the channel in compositor, and we send the display list that's send it to a new crate that we name that paint engine. And the paint engine will receive the display list and try to do some command recording, and then we'll send the display list, send the command list to render service. Okay, so let's elaborate the basic design of paint engine. So the paint engine will divide in two parts. The first one will receive display list and build the property tree and build the paint ops. And also it maintains a resource such as image and font. And after the paint ops is created, it will send to the recording part. So the recording part will call the join APIs that are provided by OpenHarmony. Okay, so because the recording part is written in Rust, and the interface and the render service provided, the interface is written in C++. So here we need a FFI here. And so node manager be responsible for managing ith node resource. So it will create the ith node and update and destroy. Okay. So after that, the ith node tree will send to render service, and the render service will do the final rendering work. Okay, so here is a simple example about how to create an ICE node and do the command recording. So here you can create an ICE canvas node. In the canvas node, there is a member function that named draw on node. In the draw node function, you can put a callback function. In the callback function, you can get the join canvas. So when you have the canvas, you can call the right side function that does the command recording. So here is a simple example about joining a rectangle. Okay, so the detail about join APIs, you can check the links below. Okay, so after implementing the basic functions of unified rendering, we also support the same layer rendering in Servo. So in OpenHarmony, applications using ArcUI, such as web components, load the page. So, but if the performance of the non-native UI components is inferior, you can use the ArcUI native components to render instead to improve the performance. Okay. So in the web page, you can use the same layer tag, such as embed and object. Here is the data flow below that. Here, that you can use the same layer tag in the HTML page. Then when the page comes to the DOM tree, there is an element named embed. And finally, we get the display items. In the display item, we add an item named embed, which is related to the same layer tag. So the paint engine will receive the display item, and will create another node that named ICE service node. That when it found that the item is the same layer tag. Okay. So finally, the ArcUI native components will be rendered into the ICE service node. Then we finish that the ArcUI native component will be displayed within the web page. So here is a picture that the video is the ArcUI native component. Okay. So next, here is a simple example that in the HTML, you use the similar tag, and from the developer side, use ArcTS. So there are many interfaces that are provided by ArcUI in the web component about enable the similar rendering, and you can register some functions so that you can receive the receive the lifecycle change of the similar tag, and also the input touch event of the similar tag. And a more detailed introduction you can check it below. Okay. So here is a deep demo that we rendered by render service. The page is mobile shopping homepage. As you can see here, that the CPU instructions is reduced by 15% per frame compared to web render. And also, we found some issues that need to be fixed in the future. So in the homepage, there is animation. When the animation is triggered, so there is will construct the static context and display list. So those two will take over 15 milliseconds. And the second issue is that because the full display list is sent to paint engine, not incremental. So the paint engine or the web render will take over 15 milliseconds to process the display list. So here is our future plan that we need to support more additional display items in the paint engine, and we want to enable incremental construction of static context and display list. And the third one that we want to apply layering to the display list for optimized rendering. And all the modifications have not yet been submitted to the community. So that's my content. And next part, please, Zhizhen.
Testing. Okay. I will talk about the status of WebDriver in Servo. So to begin with, what is WebDriver? WebDriver is a a standard protocol defined in W3C specification. It is meant as a platform and language-neutral protocol for automating the web browser. So for example, you can write your own code in any language to remotely control the browser to click, type, navigating, etc., just like a human being. So for a quick demo there, it's supposed to be a video, but it's highly compressed, it can't play. So can you help me play the video? This is just a simple demo how you can use WebDriver to control the window size, and you can do many other things. Thank you. Yeah, so this is a quick demo. And next, I will talk about why WebDriver is important for Servo and OpenHarmony. So the first thing is, it is a prerequisite for enabling interactive test coverage for all platforms, which is in testdriver.js. So you can, this test has some interactions such as click, scroll, key input, going forward, backward, load some URL, or take some screenshot. Right now, it's not enabled in Servo yet, but we hope to do it soon. And the second thing is, it is important for running WPT tests on the mobile platforms such as Android and OpenHarmony. Why? The motivation is that the difference of behavior between mobile platform and desktop is huge. And right now, most WPT test is running on desktop platforms such as Linux, and we want to do it on mobile phone. So what's the challenge for it? So the first thing is, the WPT server is normally run on the desktop, and we want to run on the mobile platform. So we want a way to consistently guide the mobile platform to reach the server on the desktop. And the second thing is we hope to still report the result on desktop, even though the test is running on the mobile platform. And the third thing is, right now we still don't use multi-process mode for WPT test in Servo. So that means if one tab crashes, the whole thing would crash. And we hope to have a clean environment for each test so that they don't interfere with each other. That's why we queue and reboot Servo for each test in CI right now. But for mobile platform, it would be a problem because it has a small physical shell. There would be thermal issue if you run the test intensively. And that's how WebDriver can help here. So we can set up a WebDriver server in Servo on the device such as OpenHarmony and Android, and we can guide the Servo on the mobile platform to reach the WPT server anywhere. And the second thing is we want to run tests consecutively in the future rather than queue and reboot. So what's the current status of WebDriver in Servo? And here's a statistics I collected a few days ago. So for Servo, right now we achieve 88% pass rate for the subtests. In comparison, Safari has 500 unenabled tests. That's why it has fewer total tests. And yeah, we are close to Chrome, but Firefox is almost perfect right now. And the second thing we are doing is we have just migrated WebDriver support from desktop to mobile platform. So you can run Servo on Android or OpenHarmony and start a WebDriver service there and use ADB and HDC to set up port forwarding and control your mobile phone. And the third thing is this is achieved a few days ago, we are now able to run a single WPT test in OpenHarmony and collect the results in desktop. And here's a brief future plan. So the first thing is, as I said, we don't want to queue and reboot. We want to utilize WebDriver to support fast WPT runner by reusing the instance. So this is some statistics shared by Nico Burns on Zulip a few days ago. So because we queue and reboot, we are quite far away in terms of performance for running a single test. And the current obstacle is, so for example, when we crash, we need to find a way to figure out and reboot the instance. And the second obstacle is like things such as cookie and other cache, which would affect subsequent runs. And the second thing is we want to enable test driver tests in the CI. Currently, it can be run locally. And that's all my talk.